And remember what chapter 4 is all about. Chapter 4 is about applications of differentiation. And you can say, what about chapter 3? Yes, implicit differentiation was an application, related rates was an application of differentiation, but that's what's all this about. This is all about graphing. So there are three major applications here in chapter 4 of differentiation. Although the entire chapter 3 is an application of differentiation. Graphing, number 2, Newton's method, and number 3, optimization. So these are the major topics we are going to look at in chapter 4. Okay, we talked about Rolle's theorem, so now we'll finish up 4.2 with mean value theorem. And we're going to look at basic examples, how we apply it in basic examples. So let's go back to the following scenario. We have a function. This is function f of x. And I have 2 points, point A and point B. Yes, I can extend the function. You can. It's not important. And this function between points A and B has x going from A to B. And of course, this will be f of A, as we know, and this will be f of B. So the mean value theorem has only 2 hypotheses. If you remember, Rolle's theorem had 3 hypotheses. The same hypothesis from the mean value theorem, but in addition, it had an additional one, number 3. But here, only 2. Very general. F is continuous on the closed interval a comma b. And F is differentiable at least on the open interval a comma b. It may not be differentiable at a and b, but we don't care. So here's what I'm going to do next. I am going to draw a line segment AB. Here's the line segment AB. I thought it would work better, but it didn't, so I have to redo it. So let's say this is the line segment AB. I'm a little far away from the table, and that's why. Okay, so the line segment AB, and just imagine now that I draw parallel lines with the segment AB. Another parallel line, another parallel line, another parallel line. And here, I will draw a parallel line, but that is also tangent. So the tangent is right here. I kind of missed it a little bit. Of course, this is our favorite point. And of course, this point will have an x. And its x is c. So now let's write the theorem together. The function is continuous on the interval a comma b, as you see, is differentiable on at least the interval, open interval a comma b. Then we'll say, then by MVT, mean value theorem, MVT, there exists a c in the open interval a comma b such that. So based on what I just did, what will you say? So this is the tangent at P to the graph of the function f at P. And the x-coordinate is c. So since it's an application of differentiation, can anyone help with any idea?
Could it be something just as simple as c is differentiable?
So we have to write that f prime of c, which is the slope of this line, must equal the slope of this line by construction, right? Which is f of b minus f of a over b minus a. Tell me if it makes sense before we look at our first example. Let me know if it makes sense.
So, like, what exactly is this telling us?
Very good. It tells us that for any function that is continuous and differentiable, if I want to determine, as an example, there are other applications. Here's one example, one application. If I want to determine the rate of change of the function between a and b, I can really determine f prime of c. Somehow I may not be given the points a and b. I may not have a and f of a. I may not have b and f of b. But I can still determine, without even knowing too much about a and b, I can still determine the rate of change, f of b minus f of a over b minus a. This is the rate of change of the function between a and b. I can determine it with f prime of c.
Okay, gotcha.
This is one application. There are many others. Okay. You may also find this result cross-multiplied. Like what? I normally don't use it like this, but it's very possible. Cross-multiply, and you get this. So it's this or this. Same thing. And now let's look at a few applications. Okay, so let's say problem f of x. We are given a function f of x, which is natural log x. We are given the interval 1, 4. And here is the question. Verify that the function satisfies the hypothesis of the MVT on the given interval. And then find all numbers c that satisfy the conclusion of MVT. Is this just one possible c? No. We can have several possible c's, like with the Rolle's theorem. It depends on the function, right? How it looks. So our first concern is to show that the function is continuous. Yes, I know the graph of natural log. Here's the graph of natural log. And this is 1, and this is 4. Obviously, the function is continuous and differentiable between 1 and 4. So f of x continuous on 1, 4 for sure. And number 2, f of x differentiable at least on 1, 4. We don't care what happens at 1, if it's differentiable or not. It is. And same thing with 4. Then, of course, by MVT, there exists a c in the open interval 1, 4, which means not 1 and not 4, such that f prime of c must equal f of 4 minus f of 1 over 4 minus 1. Please stop me if you have any questions so far. Anything?
You just go the teeniest bit slower.
What did I do?
Can you just go just like a tiny bit slower?
Sure. So I have to determine f prime of x, which we know is 1 over x. I have to find f of 4, which we know is natural log 4. And I have to find f of 1, which is 0, because natural log 1 is 0. And now I just will create this equation. F prime of c is 1 over c equals f of 4, which is natural log 4. There is no point in writing f of 1. 4 minus 1 is 3. And this is a proportion I'm sure you remember. If not, I'll tell you now. In a proportion, I can flip both sides. Why will I do that? Because it's 1 over c. So that's the easiest thing to do. 3 divided by natural log 4. And yes, I will make sure that this number is between 1 and 4. Otherwise, nothing we did makes any sense. So, but I will still check just in case I don't have an error. And I get 2.16, which is definitely in the interval 1, 4. It's guaranteed, at least one. It's guaranteed by the mean value theorem. So this is in the interval 1, 4, guaranteed. Is this okay? Is everyone with me? And here's another application in which we don't even, as I mentioned a minute ago, we don't even have the function. Something like, let's say, suppose we are given 3 less than or equal to f prime of x less than or equal to 5 for all x values. Fine. Then they say, show that (18) is less than or equal to f of 8 minus f of 2 less than or equal to 30. So suppose that the function, the derivative is between 3 and 5 for all x values. Show that 18 is less than or equal to f of 8 minus f of 2 less than or equal to 30. Okay, so how do I start thinking about this? If I am told, first of all, that the derivative is between 3 and 5, it's clear for all x. It clearly states, listen, the function is continuous and differentiable. It exists everywhere between 3 and 5. That's what it means. So that means that when I look at what I'm trying to get to and solve or show that this is true, obviously I see f of 2 and f of 8. So that's an indication that they really want me to look at the interval 2, 8. If the function is continuous, because otherwise it would not be differentiable. If the function is continuous and differentiable between 3 and 5, and exists, and it's squeezed, if you want, between 3 and 5, that automatically says that the mean value theorem is applied everywhere I want, between any two values that I can think of. And guess what? I'm thinking of 2 and 8, of course, because the function is continuous and differentiable everywhere. Okay, then, so number 1, continuous on 2, 8. It's continuous everywhere for all x. Furthermore, 2, 8. Number 2, differentiable. It says so. It exists everywhere. So also on 2, 8. Therefore, by MVT, there exists a C in the open interval 2, 8 such that f prime of C equals f of 8 minus f of 2 over 8 minus 2. And this is what we just wrote a minute ago about the mean value theorem. Good. Now I know that, according to this, f prime of x or f prime of c or any f prime is squeezed between 3 and 5 according to what is given to us. Okay, if that's the case, then I have 3 less than or equal to all this, f of 8 minus f of 2, divided by 8 minus 2, which is 6, less than or equal to 5. Can anyone suggest what to do next and finalize the problem? Anyone?
Multiply 6 on both sides.
Very good. Thank you very much. So we have 18 less than or equal to f of 8 minus f of 2 less than or equal to 30. And that's exactly what we were asked to determine. Thank you. Okay. That's really all I had to say from about 4.1 and 4.2. I'm hoping you're going to do or work on the homework as soon as possible and come back on Monday with more questions from 4.1 and 4.2. 4.1, 4.2. Okay, so let's start 4.3. In 4.3, we are going to look at how the first derivative and the second derivative, what do they tell us about a function? F prime and F double prime in connection to f of x. What do they tell us? What's the connection? Why do I ever want to look at the first and the second derivative of a function? What does that say about the function? So let's look at another graph. Here's the graph. I don't think that this color is too good. It's not a good color. Okay, here's our function f. I see that it definitely is increasing to a particular point. Then it's decreasing to another point. And then it's increasing. This is a quick review from section 4.1. We call this a local max. We call this a local min. And we said that a critical number of a function, if it exists, comes from two sources, either from f prime of x being 0, or from f prime of x being undefined, but f of x is defined at those points, or x values. Only critical numbers can turn into max or min. How can they turn into max or min? Only if the function changes sign for maximum from positive 0 negative. So this is the derivative. The derivative is positive and then 0 and then negative. Or it's positive, undefined, and negative. These two are specific for a maximum. What does this mean? The derivative is positive, then it's 0, and then it's negative. Function increases, reaches a peak, which is a maximum, and then it decreases. The derivative is positive, the derivative is 0, and the derivative is negative. So this is the sequence for a maximum. This will be the sequence for a minimum. The derivative is negative, the derivative is 0, the derivative is positive. The derivative is negative, the derivative is undefined, and the derivative is positive. So for a minimum, negative 0 positive or negative undefined positive. These are specific for a local min. We discussed this before. I just need to refresh your memory on it. And also we discussed the behavior of a function on a closed interval. Okay. I would like to jump to some examples and talk about the first derivative as well as the second derivative. So, in short, what does the first derivative tell us about the function? It says when the function is, it tells us when the function is increasing. It tells us when the function is decreasing. And it tells us where the function has a max or a min. So this is what we learn about a function from its derivative, where it's increasing, where it's decreasing, and where it has a max or a min. Now, what do we learn from the second derivative? From the second derivative, we learn something called concavity. What does that mean? So let's come back to our example here. See, this function opens downward till a certain point, and then all of a sudden it changes concavity and it starts opening up. So between negative infinity and this point, I'm going to call it A. Between negative infinity and A, the function is concave down. And between A and infinity, the function is concave up. This point right here is called an IP, which is an inflection point. So concavity, meaning opening upward or opening downward. Some of my colleagues say it holds water and it doesn't. So, and we'll analyze this again, and I'll analyze this also in detail. Also, the inflection point. Inflection points or point. So coming back, because I want to write it here summarized as well. Function is increasing when f prime is positive. Function is decreasing when f prime is negative. Max in this situation, min in this situation. Okay, what about concavity? So now we know that the inflection point, the second derivative must change sign from positive to negative, from negative to positive, or from positive to negative. Even if I find a point that I think and I hope it's an inflection point, if the second derivative does not change sign, either from opening down to opening up or from opening up to opening down, then that is not an inflection point. So it opens up when the second derivative is positive. It opens down when the second derivative is negative. We're going to use this over and over and over and over. You're going to get tired of it. Okay, I would like to look at an example. Let me see where I'm with time. Oh, I have to start.